要开始吗？你们那个，还是说再等一会儿？Okay, no response from my friends. Let me text. Okay. I received the command. Yeah, I should start. Okay. Yeah, let's start. GM and GN, no matter where you are now, and welcome to today's English seminar hosted by the Dapp Learning and StarkWire. Yesterday, we had a very good session from Lucas talking about the Career 1.0. I believe that all of the attendees, got the basic knowledge about the Career 1.0, and it may inspire their interest of learning the technology and knowledge about the StarkWire. And yeah, today we invite Henri, yeah, another developer ambassador, yeah, and the topic is about recursion proof. So before we start, I like to, give you some context about the StarkWire and the DappLearning community. The StarkWire is an open programmable Ethereum layer 2 scaling solution developed by the StarkWire that use the Stark validity proof to enable off-chain computation and on-chain verification. And the Stark validity proof is secure, reliable, and efficient, ensuring that StarkNet is an infrastructure built for future mass adoptions. And for the Dapp Learning, I'm from the Dapp Learning community, yeah, one of the members, and we are designed for developers to step into blockchain Dapp development, including DeFi, NFT, DAO, and any crypto projects. And we hope we could give junior developers a feasible and easy to use blockchain Dapp Learning roadmap and present some advanced developers with a platform for communication and cooperation. And please note that we are a non-profit organization. And now we launched our project in the Gitcoin 15 waves. Feel free to donate. Okay, thanks for waiting, Henri, and it's your turn. And would you like to introduce yourself and give us
Sure.
background?
So hello everyone, and thanks for receiving me. It's a privilege to be talking with all of you. My name is Henri Liuto. I work at StarkWare as a developer advocate for StarkNet. So StarkNet, as you mentioned, is a layer 2, programmable layer 2 for Ethereum. It's StarkNet. StarkWare is the company who is currently building StarkNet. And so I explain to people what StarkNet is and how they can build cool stuff on top of it. I just want to mention that if you're interested in building dApps and you want to learn how to build a dApp on StarkNet, we have a bunch of tutorials, a bunch of links that you can check online. We have a very extensive GitHub organization with a bunch of practices and a bunch of workshops you can follow, and you'll be able to write your app on the most scalable layer 2 of Ethereum currently in no time. So, and if you have any question, feel free to reach out, send us a message. We now have a Chinese-speaking dev advocate in the team, so we'll be happy to help you out, and reach out. Don't be a stranger. We'd be happy to help you. Should I share my screen?
Okay, yeah. Sorry to interrupt. So one more sentence. If you have any questions, during this speaking or speech, please, send a message in the comment area or in our Discord or WeChat group. Okay, yeah, please, your turn.
Very nice. So I'm now presenting my screen. Today, I'm going to talk to you about a relatively advanced topic, which is recursion. So what is recursion exactly? Oh, just give me a sec. And what are we going to talk about today? So I'm going to give you a bit of background on what we are, what we do, and then I'm going to talk about what is recursion, what it is we call recursion. And then I'm going to explain how recursion will benefit from, how the networks we operate will benefit from recursion. I say networks with an S because we currently have two networks on top of Ethereum that are running, which is one is StarkNet, the other is StarkX, and I'm going to talk about both and how they can benefit from recursion.
Yeah.
So first, as a background, let me explain a bit what are proofs, what are Starks, what is Cairo, what is Sharp, and what is StarkNet. So in a nutshell, what we call Stark proofs and what Cairo is are the following. A Stark proof is a way for a person to run a specific computation on their machine and generate a proof for this run, for this execution of a program. The very cool particularity, the property of this proof is that if this person gives the output of the program as well as the proof to somebody else, this person can verify the output of the program without having to run it themselves. And it sounds simple, but it's actually a very novel property in computer science. It's not something that we've known how to do for a very long time. The first concepts of computational integrity are trustless are essentially Starks and Snarks. So sum up again, let's take an example, right? So I'm going to run a program where I do generative art, right? And this art would take 100 years to generate on your computer because it's very complex, right? But I have a very big computer, so I run it on my machine and it takes me 1 hour. If I give you the output, how can you be sure that I didn't give you a random output? How can you be sure that I gave you the output of running the program?
Yeah.
In the usual world, you have no way of doing that. The only way you can verify the output of the program is by running the program yourself, which would take you 100 years. So it's not feasible. Now, the cool thing is that when I run the program, I also ran the program and I generated a proof. Now I can give you the output, so the art that was generated, as well as the proof, and you can verify in a few minutes that the art is authentic, that it was generated with the computer I used. Now, what makes this powerful is this difference in time. So let's say specifically it's what's written on screen. If a computation takes me time t, you can verify it for log t time, right? So the scaling factor is exponential, right? It takes you exponentially less time to verify the proof than it took me to generate it and to execute the program. Now, Cairo as a smart contract language is essentially it's not a smart contract language, it's a general purpose language that lets you write a computer program, right? And generate a proof very easily for that program. So the proof system I described, the Stark proofs I described, basically are essentially mathematical concepts that manipulate polynomial equations. Not everybody wants to design polynomial equations with specific properties to prove a program. So our team basically came up with a set of polynomials that satisfy a specific constraint that reproduce the characteristic of a CPU. So some basic operations on polynomials are allowed. And from these basics operation, we're able to design a higher level language, which is Cairo. This is also the reason, by the way, you can't generate a proof for an arbitrary smart contract language. You need to write your smart contract, you need to write your program in Cairo because it compiles down to a specific set of constraints for a specific polynomial. But Cairo basically lets you do that. You have a prover running the Cairo program on input X, giving the output Y, and the verifier can verify the proof, which is nice. Now, how do we use this in the blockchain world? Well, the cool thing with verifying the proof is the following. It's that verifying the proof is something you can run on a computer program, but in fact, since it's basic mathematical operations, it's also something you can do inside a smart contract. So you can write a smart contract that will verify a Stark proof. In fact, we wrote this smart contract and we operate an architecture on top of Ethereum that is called Sharp and that basically aggregates Cairo program, right? Compiles them into a single proof through a prover and then sends them to the verifier on chain. Why do we do that? As I mentioned, verifying a proof is log t time you're running your program for t, meaning that if you run your if you run a program for t time, it will take you log t time to verify the proof. If you run twice that program, right, so 2t, it will take you log 2t times to verify the proof. And the fact is that log 2t times is much smaller than 2 log t times, right? So aggregating Cairo jobs like this allows lowering the verification cost per jobs, right? So, and I'll talk a bit about that later on, about the challenges with recursion, but basically with proving, it's not just, hey, you generated a proof and verifying it on chain. There's a big engineering aspect into how do we make this scalable and efficient. And we came up with this system that is called Sharp for shared prover because you can have various entities. So here you have Immutable X on StarkX, Sorare on StarkX, you have StarkNet, the network, who basically send batches of execution of Cairo programs, whether they be for Immutable X or Sorare NFT trading transactions or for StarkNet general purpose smart contract executions. And these executions are bashed into a big proof that is then sent to Ethereum in the verifier. And the verifier is able to verify that the proof is correct and is able to manipulate each outputs of these programs. And then these outputs can have some kind of impact on chain, right? So this is the state of StarkNet, of Sharp a few weeks ago. Now today I'm going to talk about recursion. So what is recursion exactly? It's actually fairly simple. This is the state of what we do right now. Okay, you have an original program and then you generate a proof for it and you verify it. Well, now what we do is the following. We run the program, we generate a proof for it, and we run a verifier program, and this verifier is written in a provable manner, and we generate a proof that we verified the previous proof, right? Sounds simple, and it is. It's not that difficult to understand, right? Verifying a proof is just a set of mathematical operations. So there's nothing preventing you writing a Cairo contract that will verify a Stark proof, and you can generate a proof that you verified a proof. And in a nutshell, that is what recursion is, right? Does that make sense up until now?
Yeah.
And the fact is, you can go even deeper than that. You can verify the proof of the proof. You can go as many layers deep as you want. The only thing that will that is you are not going to get the same return of efficiency every time, but you can get as deep as you want. So now what we do, remember the sharp program, the diagram I showed you before. Instead of just concatenating Cairo programs, we're now, so, you have sharp and you have, different Cairo programs that we concatenate and execute sequentially, and then we get a big proof for all of these. We're able to generate a proof for each separately. So this will take less time than generating a proof for all of them sequentially, because we're able to parallelize these. And then we just have a batch that aggregates the proof and generates another one. So we can have various programs that we generate in parallel, right? So in other words, you can apply recursion sequentially, or you can also apply for parallelization of tasks. Now, obviously, why do we do that? Because doing this allows to reduce proving time for the verifier. And as you know, since the verifier in our case runs on the Ethereum virtual machine, it has a cost. It has a gas cost. And so having a leaner verification makes it more cost effective and makes it cheaper for the user in the end, which is what we care about, right? Now, what can you do with recursion? Now, so that's the theory. Now, let's see how we will apply it in real life and how we've started applying it in real life. Well, the first thing is that it allows us to reduce gas cost on the networks we operate. The reason for that is that basically, there's a gas block. I mean, there's a gas limit per block on Ethereum, and I think there's a gas limit per transaction. And so even if running your program takes T time, log T, if T grows, log T still grows, right? And so there is a limit into the dimension of T when you generate a single proof for a Cairo program if you want the Ethereum to verify it. So technically this meant that there was a scalability ceiling into what we were able to do with StarkX, and there was a gas cost. We couldn't go lower. Now, and for example, here in this scheme, so for example, you have T steps, right? So you have here in the verifier, you are forced to run program A, go through T steps, you're forced to prove it, and then you have to run program B, and then you're forced to prove it. So the cost of verification is spread over program A, and then another verification is spread over program B. Now, what we're able to do is basically, instead of doing that, we're able to have program A, and we generate a proof for program A, and program B, and we generate a proof for program B. And if instead of verifying 2 times in Ethereum, we verify them 2 times in a Cairo program, and we generate a proof for that verification, and we send this to Ethereum. All of a sudden, instead of having one cost of verification spread over program A and one cost of verification spread over program B, we have only one cost of verification spread over both programs. So you basically are able to divide and amortize the cost of verification over your programs, which in the end translates to savings for users. And this is something you can verify, like you can you can do much at a much higher level, right? Because you're basically able to do this various time above. You know, you can have program A, program B, program C, program D, and as soon as you hit a specific size, you just verify it, get down to log T, and then you can aggregate these, and you're able to, in a sense, scale your proving cost and amortize it much faster on all your entities. It basically becomes a game of how far you are in the recursion chain, and you can define the cost per users depending not necessarily on the actions you make in the chain, but based on your distance to L1, if I may. Basically, the more proofs between you and L1, and the higher the complexity you can get in your program. Then another thing we started using recursion for is latency. So this is the program I showed you before for Sharp. And so basically what we had is we had these different programs, right? These different projects were running payloads in parallel. Each of them were running their network in parallel. And these proofs were then sent to the prover, who would have to then generate a big proof and then send it on chain. This meant that, for example, imagine that each proof is generated every 8 hours. Generating a proof takes time. And so every time a job at, say, for example, immutable X was finished, so say they had gone through 100 blocks, then at that point, the 100 blocks were sent to Sharp, and then Sharp would wait for the same thing from StarkNet, from StarkNet, and all of these were aggregated, and then a proof was generated. And this would take a long time because it takes it may take a few hours until it is published, right? Now, what we're able to do with recursion is the following. Every time a job is received, or even intermediate jobs can be sent, you know, we run a recursion job. And so instead of having to run the job before sending it to Ethereum, instead of having to concatenate it, you can start parallelizing and take jobs and generate proof for these. And now when the last job arrives, you can even aggregate these into smaller proofs. And when the last job arrives, you can just generate a proof, generate another proof for everyone, and then send it. So basically it allows, instead of waiting for everyone to be here and then generating a proof, it allows compacting stuff as they go, so that once you say, okay, the train goes, everything that needs to be compacted in the final proof is smaller, and so you have a shorter time to mainnet. Right?
Yeah.
And this is in a sense, and this also saves cost, obviously, because this final proof here is the verification of a virus subproof, so it's even this even is cheaper. All right, so these are things that we're using right now in production. This is something that went in production recently, and we're already using it to decrease latency and to save cost. Now, the other concept that people get really into is the concept of L3. And I'm gonna get into it in a second. Everything that I'm referring to, so recursion is the fact to generate a proof that you verify the proof, right? Now, what we call fractal scaling is the fact that this technique allows you to scale your network in a bunch of dimensions. You can scale it in the time dimension, you can scale it in the complexity dimension, you can scale it in the layers dimension. And this is the last one, this point I want to talk about. Right now, you have Ethereum, and on top of it, you have a bunch of networks. So there's StarkNet and there's StarkX, and there are various instances of StarkX. Maybe, I mean, one day we will have a Cairo verifier operated on StarkNet. And so basically the architecture you have on top of Ethereum, you know, Sharp, which I presented earlier, you will have Sharp on Ethereum, but you will also have a Sharp entity on top of StarkNet. And verifying a job on StarkNet, on Sharp on StarkNet, will be cheaper than verifying a job on Sharp on Ethereum, because it's further away and you generate a proof after that before you send it to Ethereum. And once you have a Sharp operated on StarkNet, it allows you a bunch of stuff, and it allows you to run networks on top of StarkNet. And if you operate a Sharp operator on that network, you can run a network on top of this one, and so on and so on. What is really interesting is that these networks that you'll be able to run on top of StarkNet, there are a few things. The first one is that they can be of any kind of architecture you want. StarkNet is a L2 on top of Ethereum, and it is an L2 that is written in Cairo, but you could implement other kinds of VM in Cairo. You could have StarkNet, of course, but you could have StarkX. You could implement a ZK VM written in Cairo. You could write an Orbit VM written in Cairo, and you could generate a proof for that. And so basically you could have on top of StarkNet different subnetworks with different characteristic. The other thing that is really interesting with recursion is that proving that the network executed correctly basically allows operating a network without having to trust the operator. Because since you're generating a proof for the execution of that network, there's no way the operator can cheat. The operator either behaves honestly or he is not able to generate a proof. There's no way for him to generate a proof where he cheats, right?
Yeah.
And one big narrative in the blockchain space and in Ethereum for the past few years has been enterprise chains. You know, let's set up a permission chain, let's set up a chain for a consortium and stuff like that. And this never really took off. Why? Because what you want in a blockchain network is for people to trust what happened in a smart contract. When a chain is controlled by a set of validator, if it wants to trust something that was done by another set of validator, it basically means that they need to trust this other set of validator. In our world, it's the same as having the same set of validators. And this does not work because if it will work, you wouldn't need two sets of validators. With proofs, you actually don't have this issue because a set of validator can trust the output of another set of validator, even if he doesn't see the data, because there's no way they could cheat. So once they generate a proof, they can believe it. And now they have a way to communicate with each other. They have a way to trust each other based on math and not based on game theory.
Yep.
So there is actually a future where these chains, these proprietary chain, these permission chain, however you want to call them, they communicate and they interact with each other. And even better, it lowers the barrier to entry to run such chains, because to run a consortium chain or an app chain today, you need to be very mindful of your validator set. You need to lobby so that people will run the validator. You need to make sure they don't forget it. With this kind of networks, you can run it on a single machine and people will still trust you because there's no way you can cheat. It's not that they will trust you, they will trust the math that you cannot cheat. And so the barrier to entry to run a network will lower dramatically. So you will have a multi-chain future, a multi-network emerging with this technology. Now, another thing that is really cool with recursion is that we get to have a simpler solidity verifier. So let me take a step back on this one. So a bit earlier, I described Cairo as a CPU that allows you to run generic programs, right? That get
Yeah.
compiled to polynomials. You really have to, if you think about the architecture of a computer today, what is a CPU? What is your computer? At its core, it's transistors. And basically what they do is add stuff and make
Nice.
differences.
Yeah.
And they have a very simple set of constraints and capacity. But on top of this, we're able to build more complex structure and more complex structure until you get to a relatively high level um, language. Well, so based on very simple basic arithmetics, you're able to build complexity. Polynomials are the same way, in the sense that on top of polynomial, you're able to encode basic operations and then build complexity on top of that. And the same way that modern informatics evolved by leap and bounds, Stark systems are evolving the same way, meaning that the first computer circuits or the first circuits that evolved were really electronic circuits with a few transistors to do one specific operation, right? And the first iteration of Stark proof system were the same thing. We would write a program defined as a set of polynomials that was very specific for that program that would allow us to generate a proof. And it worked well, but eventually this is not very flexible and it's very cumbersome to read, just as a specific ASIC is not very flexible and hard to design. So we came up with different architecture to do some different operations. And so we arrived with Cairo, which is a general purpose CPU that allows you to write arbitrary operations. But if you think about it in your computer, there are other electronic circuits than just a CPU. For example, you could have a GPU that is specialized on special types of operation. And we have the same kind of concepts in um, Stark proofs, in the sense that some operations will take time to execute on a general purpose CPU such as Cairo. But if you write a specific circuit for it, if you write a specific polynomial for it, then you get to execute it much faster.
Yeah.
And this is what we call built-ins, right? So a built-in is basically a set of constraints on a lower level than Cairo that allows you to execute specific mathematical operations for a cheaper cost than if you were to run on the more general global purpose CPU. Now, the thing is, there's a trade-off with built-ins because we're able to generate a proof for the CPU, we're able to generate a proof for the built-ins, but this takes some space. Having more built-ins, having more components will lead to a higher proof size in what we call the layout, because the solidity verifier will need to be able to interpret the proof that comes from these built-ins, right? So the more built-ins, the more complex the solidity verifier gets. Okay?
Yeah.
Now, what we get to do though, and this puts an upper bound, like it puts a limit on the number and the complexity of built-ins we can get in StarkNet and in Cairo. Now, having recursion means that we can write an intermediate verifier in Cairo that will have a large layout, right? That will take outputs from many built-ins on layer 3, for example. And on layer 3, you'll get to generate some operations much faster because you'll be able to use these special built-ins. And these built-ins, they will be verified by StarkNet. But in order to verify these built-ins, you don't need the specific layout. You can use Cairo to verify these built-ins. You can use the general purpose one. And so this means that you can move the complexity of the layout to StarkNet and remove it from Solidity, where things are expensive. And so you can have a simpler verifier verifying complex stuff. it sounds almost like magic because you basically have complexity and you're able to boil down complexity to smaller and smaller operation until they're very cost effective on L1. So for example, you could have check built-ins, and so you could have the check built-ins on L3 and then verify that the check built-in was executed correctly on L2, and you don't need to have the check layout on L1 to verify that it executed correctly. So it saves you money and time. And in a nutshell, that's what I wanted to discuss about the recursion, how we're applying it today, how we're using it, and what we think it can bring in the future. So to sum up, it's going to reduce gas costs for users of all the systems using Stark proof. It's going to make proofs bigger, and so it will allow to add way more computational capacity in a proof, and to a certain extent, it will grow the computational capacity of Ethereum. Second, it will reduce latency. It will allow the proof for a block to be generated much faster. It will allow the proof for a block to reach mainnet faster. Let's say it that way, right? Finally, it's gonna allow the emergence of L3s, so layers on top of layers on top of layers, which will basically allow apps to decide how much their app will cost based on their distance to L1. And finally, it will even allow to have a simpler verifier on Solidity, which is great both for cost purposes, but also for auditability, because a simpler verifier, a Solidity verifier, makes it easier to for people to audit.
Yeah.
Right? Now, where are we with that exactly? How much of it is fiction? How much of it is reality? This presentation was done 2 months ago, and it says production in less than a month, and it is. Currently, we updated the Solidity verifier for Sharp on Ethereum, and it is now able to interpret recursive proofs. So we now are able to batch 8 times more transactions than we used to in a proof. So it means that the cost is even further reduced for the operator. And it means that latency is also going down. Now proofs reach mainnet up to 4 times faster than they used to. So it's a better user experience for users. They're able to withdraw their fund much faster. They're able to mint their NFT for a lower price, and so on. Now there are still a bunch of optimization we could take. I'm not going to get too much into them, but I'm not going to get into the flexible hash commitments. But there are some optimization we could take around state update, which is still one of the bulk of the cost for StarkNet smart contracts today. And yeah, another thing we could do is just improve recursion, do better recursion, and then recurse over that, and improve recursion, recurse better, improve over that, and recurse better. So this is basically what we're going to do. I'm not going to get into that because I'm not sure I'm going to be able to explain it correctly. Now, I'm going to explain what we could do is state updates and data compression. So the principle of a ZK rollup compared to what we call a Validium is that when you do some operation on a ZK rollup, the computation is verified, but if you want to have full security, you still need to have the data to reconstruct the state of the network at a given point in time, right? In order to optimize this means you would basically have to publish the state of the network every time you publish a proof. But if your state grows, it's not very efficient to publish it every time. So what we do is we publish state differences. Basically, every time proof is updated to mainnet, we will publish, hey, here's the difference with the former state. So it allows us to have just the diff with the former state. Now, when you think about it, before what we had to do, say you had, we used to send like a few hundred blocks of StarkNet, we would have to send the state diffs from block 1 to block 2, then from block 2 to block 3, 3 to 4, and so on. And all of these state differences were sent to the verifier, and the verifier would verify all of these. Now, if we're able to generate a proof for, so that's basically what it is, right? So for each block, we would have to store the state diff. Now, if we were able to generate a proof for going from block 0 to block 2, instead of storing 3 state differences, we would be able to store only 1. And if some actions are repetitive, or if the same cell is manipulated over and over again, this leads to cost saving for the end user. I'm not sure if that makes sense. Let me know if you have any question. So yeah, I'm reaching the end of my presentation. So to conclude, I'll just say that, recursion is a great tool. It's a fascinating concept. I think recursion really brings to the forefront why Stark proofs are fascinating. Thinking, oh, I can prove a program and it takes me less time to verify it than to run it is kind of a fascinating concept. But once you add recursion on top of it, it really drives the point home that there's some kind of magic there where you actually are able to prove you can verify the work of somebody for a cost that gets lower and lower in time, which is really interesting. So it allows boosting the performance from the networks. It allows to have more complex behaviors on top of StarkNet, and it is something that is live today that will get better with time. And then that's it. I reached the end of my presentation. I hope this was clear. Let me know if you have any question.
Yeah, yes, thanks,
Did it make
Henri.
sense?
Yeah. I think it's easier than I thought before I joined to this session, because I'm not I'm good at mathematics. I'm afraid that I have to know some knowledge about polynomial or some long calculations, and but not. Yeah, everything is clear, and I think I can get the higher level about your recursion. I can say it will be powerful, and especially helping us save guys with more proofs capacity, but keeping the same the same capacity, the T. Yeah. And yeah, one interesting concept I learned is layer 3. Yeah. And I think it's quite a big idea about this part. I would regard it as the blockchain VMware or VirtualBox. In the future, maybe we will have such an infrastructure provided by the StarkWire. Yeah, that's my feeling or what I have learned from these sessions. And I received some questions, yeah, from our audience. Maybe we can. We have 5 questions, and
Wonderful.
Yeah, nice. Looks like we have many members interested in this part.
How many people are on the stream, more or less?
Currently, in Google Meeting, we almost have 10, but they also do forwarding in another platform, like open to more Chinese people. Yeah.
Super
And cool. Yeah, nice, exactly. So what is, one of members willing to know the specific math. So what kind of algorithm is used to implement such recursion?
The same algorithm that we use to implement Stark proofs. That's the beauty of it. It's just the same algorithm applied over itself. So if you want, I can give a quick, let me try to make it very high level how Stark proofs work. The idea behind a Stark proof is that I have a polynomial with 1,000,000 factors, right? And I want to prove to you that I know all the solutions to this polynomial, all of them. I know all the roots. But I don't want you to have to calculate the 1,000,000 steps for this because it will take you a long time, and it's not. And I don't want you to do all of this work.
Yeah.
So what I'm gonna do is I'm gonna run a computation trace where I'm going to specify all the inputs for my polynomial and all the outputs, right? And I'm going to specify all the roots where, I'm going to specify all the roots. So the output for every line should be 0, because if I know the roots, then the polynomial should be canceled every time, right? So now I have a list of factors and a list of zeros. Now on this list, on this data, I'm going, and on the list of zeros, I'm going to apply an error correction code. Error correction code is a kind of mathematical mechanism that allows you to transmit a bunch of data and make sure that if part of it is lost, you can retrieve the data, the full data that was sent. And one way to do that is, for example, just to broadcast the same data 5 times, and hopefully you'll get part of it. Now, there are much more complex error correction code, and one of them is the Reed-Solomon error correction code, which basically makes it so that if you want to transfer n data, you will emit more than n. Let's say you emit 16 times n, but if you retrieve any n data in the data that was just transmitted, you're able to recover the full n that was transmitted in the beginning. Okay? The way they do that means that every data that is present initially should be present somewhere in the 16-time outputs, right? Now remember, what am I transmitting? Just a bunch of zeros. Now, so on the other side, you should have the same thing, just a bunch of zeros. But if somewhere in my bunch of zeros there is something different, say a 1, for example, then this error correction code will make sure that this one will be replicated in many places in the output of the error correction code. In fact, if I change just one cell, I have a 5% chance of picking it if I take one of these outputs randomly, right? Given it, so say it another way, I have a bunch of zeros there. If I put in one place something else than a 0, and I pick a random value on the other side, I have 95% chance of I have 95% chance of picking something else than a 0. Okay? So still, 5% is not that much. So now the trick becomes, hey, look, you committed to a bunch of zeros. And on the other side, if there was something else, then I should be able to see it. So I'm going to pick one value, and if it's not a 0, I know that you cheated, right? So I'm going to pick it once. And if I find a 0, I know that I'm 95% sure that you did not cheat. 95% is not that much, though. So I'm going to pick another one. And then I am 95 times 95% chance, right? So in other words, the chance that you cheated becomes 5%, then 5% times 0.5, 5% times 5%. And so if I do that a few times, I'm literally sure that you did not cheat. And so basically what I do is basically that. I take this bunch of zeros, I generate a trace, and I applied the error correction code on top of it. I commit to all the values. You pick a bunch randomly, and then you're sure I didn't cheat. And if you make this calculation, like say 16 times, you're fairly sure that you're very sure I didn't cheat, and you only calculated the roots 16 times instead of a millions. Now, yeah, in a nutshell, that's how Stark proofs work. And this protocol can be re-implemented if you have a general purpose programming language, and Cairo being a general purpose programming language, you just implement this on top of it, and that's how you recurse it. Does it make sense?
Yes, yes,
Cool.
totally makes sense. And yeah, thanks for explanations. And yeah, I think our participants have answers about this part. And next is about the building procedure. So what's the biggest challenge during building such a recursive layer or such a method? Is it kind of mathematical proof or some engineering issues?
I mean, the theory is here, so obviously writing the program to do so is a challenge, but I think the engineering part, figuring out how to set up the infrastructure to receive jobs and then condense them and optimizing them to make the most out of recursion, this is a very non-trivial part. And before you're able, like the concept of recursion is interesting, how you apply it to derive savings and lower latency is a challenging part also.
Okay, I see. Yeah, it must be a very complex system, and yeah, a lot of members putting efforts on this part. And let's see the next. Yeah, it's question about the polygon. How does the StarkNet recursion compare with Plonky 2? Plonky
Sure.
2? Yeah, such a name.
So
yeah.
that's a good question. I don't have a lot of insight on this. I'm not super sure. So take what I will say with a grain of salt, but in a sense, Plonky 2 is one step of the whole process I've described, which seems to be very efficient. One way they achieve that is that they have a smaller field of calculation, which is, so in a sense, when you write code in Cairo, you can have a number from 0 to 2 to the power of 251, more or less.
Yeah.
And by choosing a smaller field and having smaller integers, you get to have some kind of savings. I would say the biggest difference between Plonky 2 and what we have is that what we have is in production, and Plonky 2 is a research project, which is really interesting. But so far, it's still research. There's no way to really use it.
Okay. Still in the paper.
I mean, it will come to life for sure. I mean, they're bright
Yeah.
folks, I'm sure. But for now, it's really hard to have proper benchmarks because there's no way to use it.
Yeah. Okay. Yeah. I think what we need is something in reality. Yeah. That's the true thing we can use in our daily life. Okay. Thanks for the explanation. And the next, yeah, I think you may, I mean, previously you mentioned, I mean, at the end of today's demo, you mentioned the state data, yeah?
Yeah.
And the data compression. Did we do kind of recursion during this part?
I mean, aside from what I described, unfortunately, data storage is not really something execution will affect. So for now, so we don't like, this is one avenue of optimization we have, but that's about it for now.
Okay, I see. Gotcha. Cool. And one last thing, it's a little wild from my side. What difference is recursion going to make on StarkNet in the development of ecosystem?
I think that there are various ways you could have it. I think it will make the user experience better because it will lower cost and lower latency. Second, it will make developers able to run arbitrary code in their smart contract. Right now, if you ever wrote a Solidity smart contract, you can't really run arbitrary code. You're bounded by what the EVM can do and what the network can do. With recursion, you could imagine running a program on a supercomputer and use that output in a blockchain network, which is crazy. So, I mean, you could have weather forecasts on the blockchain. How crazy is that? So it will,
Forecast. Okay.
yeah. I mean, like, you could have AI on chain. You could have provable AI executed off chain, proved on chain. So you can really push the boundary of what is done is doing. I'm sorry, what is done on chain. There will be a whole new wave of app-specific chains where people will just run their own chain because it's easier for them to do so, or they want to have privacy because they don't want to push the data on chain. And all of this will be done in a trustless manner. And finally, I think there will be a big wave also of privacy tools, because privacy on Ethereum, for example, is relatively expensive because
Yeah.
executing complex mathematics is expensive. Now, if you're able to have computation for cheap, then you're able to implement complex privacy protocols and execute them on Ethereum. So I think we're going to see a whole new wave of privacy protocols emerge and be implemented at the Dapp level. So I think it's going to be really interesting.
Okay. Okay. Yeah. I'm excited about what you said before. Maybe in the future we may have, like you said, AI on chain and yeah, some big stuff. And yes, and
Just
I
wanted
think
to share this repo.
Yeah.
If you are interested in building on StarkNet, make sure to check it out. It's here. Let me try to see if I can come up with a QR code, right? This one.
Yeah.
So check this. Oh, you can't see the QR code, but check this tutorial. It will guide you through what Cairo is and how you can build on top of it. And it's fun. You collect points. So go take a look and figure out if Cairo is easy. It is.
I mean, step by step.
Yeah, exactly.
Okay. Okay. And last, I think I still have, I mean, a personal question about the slides.
Sure.
Could you please return to the slide 22?
Sure. Wait a sec.
Okay, nice.
Yeah.
Yeah. So in this slide, do we have any limitation to the number of, I like to say, so theoretically, we can wrap or aggregate all of the verifier as many as we want, right?
Yeah.
Okay. Okay, I see. So currently, do we have kind of data like in the building progress? I know we cannot reach that limit. So do you know the exact number during the implementation, or
Unfortunately,
the max?
no. I don't have an exact number. I'm sorry.
Okay, it's okay. Yeah, I just driven by the curiosity. Yeah.
No, sure, and it's great questions, but I don't have this information, unfortunately.
Okay. Thanks, Henri.
Sure, happy to have you.
Yeah.
I mean, happy to
Yeah.
be here. And yeah, you guys know how to reach me. Feel free to ask any question, and I hope to do this again soon.
Yeah. Thanks. And I think after 2 days of studies, Henri and Lucas gave us a good presentation about the Starkware and especially the Cairo and the recursion. And I believe all of the participants must have a deeper understanding about this part. And at last, many thanks to Henri and Lucas for their patient explanations. If you have any questions or issues in the future, you can reach out to them or ask questions in the StarkNet communities or DappLearning community to get some helpers or ideas about that. Okay, I think it's done, and thanks for all of the participants, and as well as Henri. And thanks for StarkWare and Dapp Learning and giving such a great event to us. And enjoy the rest of your day. Yeah.
Thank you. Have a good day.
Thank you. Bye bye.
Thank you, Henri.